Please go ahead.
Right. Thank you, Mark. First of all, thanks for inviting me. I really appreciate the chance to talk about my research again. Okay, so before I start, just letting you know, if you have any questions, by all means, you can stop me at any moment. I have plenty of time, I can assure you. So, all right. So this is the work I want to talk about. I want to talk about what I've been doing for the last year and a half or so. And this has been the product. So it's about noisy coherent population trapping, which I'm going to be explaining, hopefully. And I guess we can start the motivation. All right, so I want to start with the most basic motivation, which is the decoherence that happens when we prepare a qubit for any application. So typically, the one decoherence that you always have to take account of is the one by the quantum vacuum. Now, when I say decoherence, of course, I mean, let's say your qubit is prepared in a superposition state, and what happens is that over time it gets to its, let's say, ground state, right? So that's what I mean by decoherence. But typically, this is what would happen when your qubit is coupled to a quantum vacuum, but also similar things could happen when you also include the effect of the medium or the environment in which you're implementing the qubit. So that's also an important issue. Now, the way we model the environment, since we're going to be interested about this problem, in terms of the noise, is going to be through a classical model. That is to say, a classical, let's say, fluctuating magnetic field, right? So that's going to be the way we model the environment noise onto the qubit. So one thing you can talk about, for example, is the correlation function of that noise, right? So here I give you an example. This is just a correlation function that's an exponentially decaying one. So the longer you wait, the lesser correlation there is between the noise at time zero and the noise at time t in the environment. And of course, this noise model has some parameters, right? It can be the sigma and the tau in this case. So the question then becomes, well, how do I know the noise parameters? Now, what the motivation of this work is to estimate the noise parameters using a specific system, not a qubit, but using a three-level system, which I call a lambda system, because it has a formation of a lambda, and it's driven. So it's driven by laser fields, as I'm going to show you. Plus, we're going to be forming a theory of coherent population trapping that's going to help us to do the noise parameter estimation that I just mentioned. As a bonus thing, I'm also going to mention an application in something else, which is dissipative qubit state initialization. So I'm going to show you that as well. All right, so I guess we can start with coherent population trapping. So let me first tell you what this is, because you're going to see this word over and over again. Just for your attention, when I say CPT, or when you see CPT, I don't mean the usual CPT that you're all familiar with. I mean the coherent population trapping. So just for your attention there. All right. So imagine a three-level system. You have one excited state that's coupled to two ground states. So this is a three-level system, and you can drive this system through two lasers. And this is the configuration that I'm working with. So here, it is very well known that there's an equilibrium state for the dynamics as soon as you include the coupling to the vacuum. The equilibrium state is going to be a superposition between the two ground states under specific conditions. So specifically, when the two photon detuning is zero, so to speak, then the steady state solution is only on the two ground states. So that is to say, there is no excited state population in the steady state. So if I want to write that one down, the equilibrium state will look like this, where the so-called dark state, which is the equilibrium state, is perpendicular to the excited state. So it's not in the same Hilbert space. And it's very interesting to note that also the equilibrium state is a pure state, which is not expected typically. All right, so you can of course describe this dynamics using a master equation. So what you would have here is, I forgot the minus I next to the commutator, but excuse me for that. So the way you would describe the dynamics is by the usual term here, which is the Hamiltonian of the lambda system that we have, plus the derive with the two optical fields, and plus some third term, which describes the coupling to the quantum vacuum, where that third term is given by the usual Lindblad form, right? I didn't want to mention more specifically what those operators are, but they will just take your, but they just include the coupling with the vacuum, let's say. Or, okay, so this is coherent population trapping. You're basically trapping your population in the two ground states, in the superposition of the two ground states. Now, I want to tell you about a very important picture for systems like this, like a lambda system that's driven by two lasers. And it is based on a change in the basis. The new basis that I'm going to be talking about is called the dark state, the bright state, and the common state basis. And they're special for a very specific reason. So on the left, you see my three-level system, right? This is the three-level system. Again, I have my two optical fields. The coupling strengths or the Rabi frequencies are big omega 1 and omega 2. And those two lasers, of course, have some frequencies themselves, omega 1, omega 2, and some phases, phi 1 and phi 2. All right, so there's a transformation of the basis that takes you from this picture to a picture where you have two independent systems, an isolated one-level system that's unsurprisingly also my dark state, which is the equilibrium state, and an isolated two-level driven system with an effective Rabi frequency, which is given by this form. And the two states where this drive is being taken is between the so-called bright state and the common state. Now, the way that those states are related to the ground state, the first ground, second ground, and the excited state is given here, where the parameters theta depend on the Rabi frequencies. So specifically, the tangent of theta is going to be the ratio between the Rabi frequencies. I'm going to tell you more about that later. So that's for the basis. It's very important for you to remember the dark state because we're going to be encountering over and over again in this slide, in the next slides. Also, as a important reference, I would suggest for you to look into the one I have here if you're looking into transformations like this for a lambda system. All right, so that picture is going to be important. So now let me tell you about on what system I'm going to be looking. I'm going to be looking into the application. So I'm going to be specifically taking the so-called Nitrogen-Vacancy center as my medium for application. There are a few reasons for this, but first let me tell you what the Nitrogen-Vacancy center is. So Nitrogen-Vacancy center is basically a point defect endowment where you take two nearby carbon atoms and you replace one of them with one nitrogen and the other one you leave vacant. And what's going to happen is you're going to have an electronic structure formed in the vacancy. And that's what's called the electronic structure of the Nitrogen-Vacancy center. All right, so why am I dealing with this system? Well, I mean, there are a few reasons, but two reasons that I'm interested in specifically. The first is that the electronic structure is rich enough for me to be able to isolate a three-level system that's almost closed, except for, of course, coupling to the vacuum and being affected by the noise. So this almost closed lambda system is determined by those three states. This is the excited state, and those are the two ground states. These are just some group theoretical way of writing down the states. You can imagine them as excited, ground 1, and ground 2 if you want. So that's one reason why I picked an MV center, a Nitrogen-Vacancy center. The second reason is that it's relatively easy to control because the coupling, I'm saying the coupling, laser, the fields that you need to excite the ground states to the excited state are actually of the order of an optical field. Specifically, it's actually a red laser frequency. So it's really handy to use. It's very easy for experimentalists to control comparatively. So that's a second reason. Now, the interest of this work is, of course, based on trying to understand how the noise will affect the process that I'm looking for, specifically coherent population trapping. So I'm going to be looking at the noise produced by the diamond onto the nitrogen vacancy center. That noise is going to be mainly coming from the carbon-13 isotopes, and the reason for that is being that carbon-13 isotopes have non-zero spins in their ground nuclear state, whereas the carbon-12 isotopes, which are much more common in diamond, have 0 spins in their ground state. Therefore, the one that produces noise the most is the carbon-13 ones. And that's the source of my noise. So basically, I have a spin bath here acting on my lambda system. And again, I'm going to be modeling the noise as a classical field. So here, basically, you can think of it as a fluctuating magnetic field that's affecting the lambda system. And that fluctuating magnetic field has some time correlation, which I do not specify, right? I don't need a specific form for it. I just need to assume that it's a stationary noise with some zero mean. All right, so this is the model I'm going to be looking at. All right, so let me tell you what will change if we take this model and we take into account that we have noise and start looking at coherent population trapping. So, of course, without noise, you would expect there to be no excited state population, right? The reason is, well, of course, because coherent population trapping is going to happen. So since coherent population trapping will trap your population in the ground states, there is not going to be any population left in the excited state. So that's something that we expect. Now, when you introduce the noise by the spin bath specifically, you are going to see some excited state population. And that's, and I'm going to be talking more about that later. But for now, that's what you're going to see. And in fact, if you want to describe this process, you will have to use a time-convolutionless master equation. So you can describe it using an equation that's very similar to what you've seen for the one that describes a noiseless coherent population trapping. The only difference is this term you see here. Let me just, yep. Okay, the only difference is the term you see here. And this is due to the coupling to the spin bath noise. So just to remind you, this is the usual dynamics of the lambda system. This is the one by the quantum vacuum, and this is the one by the medium acting on the system. So this has a specific form, of course. I can also show you what that is. So it has a typical Lindblad form where Z12 is given by the operators of the 2 ground states. This is the first ground state, this is the second ground state, and alpha is a parameter that depends on the correlation function of the noise. So that's what we have here. And remember, the unknown parameters of our noise are implicit in the correlation function. The correlation function can have some form, for example, the one I showed you before, and there will be some unknown parameters there that we might want to specify. All right, so this is what we would have when we include the noise. All right, so let me, for example, show you how the equilibration dynamics will look like when you look into different kinds of baths in this scenario. So first, I just want to tell you how I define the correlation time. So a correlation time, you can think of it as the time that's required for the correlation function to become 0, because typically correlation functions decay in time, and if you wait for long enough, quote unquote, that time being the correlation time, if you wait long enough, that correlation function is going to get to 0. So that's how I define my correlation time. And here, as you can see, I look into baths with two different correlation times. Of course, I assume a model for my correlation function, and these are the 2 different times. So I'm basically looking at a fast bath, fast equilibrating bath, and a slow equilibrating bath. Now, for the fast bath, you see a behavior like this, where where on the y-axis I have my excited state population, and on the x-axis I have the time. So you see a behavior like this, which means that your system is tending towards a noisy coherent population trapping. First of all, why am I saying noisy? Because this is not tending to 0 exactly. It still has some residual value, which is above 0. So it's going to be a coherent population trapping, but it's not going to be perfect because there is still some population left in the excited state. Now, this is for a fast bath. For a slow bath, you're not going to see something like this. You're going to see a behavior where it's still equilibration, but it's going to tend to a value that's not even close to being zero. So these are different circumstances that can arise from this equation that we have here. And this is important for me to show you. So it's quite important. Also, just to let you know, I've suppressed the oscillations here. So if you were to look at the actual dynamics, there'll be some oscillations around these two lines. All right. So with this said, I want to tell you a little bit about the intuition behind why the dynamics looks like this. So to do that, I want to get back to the dark, bright, and common state basis, because this is always a good picture to describe a lambda system in. So first, let's look at the left. So on the left, we have the dark, bright, and common states, right? And I have my effective coupling between the dark, bright, and the common states. And I also draw my two couplings between the common and the bright and the common and the dark due to the what's the word I'm looking for? Due to the coupling with the vacuum. So so this is the situation that we have without the noise, right? This is a typical coherent population trapping scenario. So this is very similar to optical pumping in a sense, because what's going to happen is that if you have an electron in the excited state or the common state, it's going to go down. It's either going to go down to the bright state or it's going to go down to the dark state. If it goes down to the bright state, it's going to get excited again due to this coupling, and it's going to go down again. So this is going to happen over and over and over again until it ends up in the dark state. If it ends up in the dark state, it's not going anywhere because there is dark state, oops, I'm sorry, because the dark state is not coupled to the bright or the common states. So if it ends up in the dark state, that's it for that electron. And that's why, that's the real reason why we have coherent population trapping, if you look at it from this point of view. Now, if you include the noise in this picture, we can look at the right-hand side of the slide to see what will happen. So here, if you include the noise, it turns out that the noise will effectively couple the dark and the bright states, mediated by the fluctuating magnetic field that we have. So we are no longer going to have the dark state as our steady state solution, because that state is eventually going to get coupled to the bright state. And this alpha is the same alpha you've seen, just as a reminder. This is the alpha I'm talking about. It's a parameter in my master equation. So that alpha is going to couple these two states. All right. So, and that's exactly why you don't see a dark state anymore, because that state is not isolated. It's coupled to the bright state. All right. So that's the intuition. Now, let me tell you the main result that follows from our equations. So here, this is the main result. I wanna do this slowly. So let's look at the left plot first. So this is the y-axis denotes the excited state population again. The x-axis denotes the detuning of the two photons. So one of the photons, I'm saying two photons, I mean the two lasers. So one of the laser fields are taken to be to have a detuning of 0. So when I say the detuning delta, I mean the detuning of the second laser field. All right. So, oops, excuse me. All right. So here, what we see, first of all, at 0 detuning, we see without the noise, we would have seen no excited state population, right? If you look at the blue plot. So we would have seen no excited state population, and that corresponds to your usual coherent population trapping. Now with the noise, if you look at the dotted line, you would have some residual excited state population even at the 0 detuning. So that is our noisy coherent population trapping state. And if you were to vary the detuning, of course, what you're gonna get are also other steady states, but the excited state population, of course, is gonna be different. So you're gonna get a curve like this for the noisy case, and a curve that goes like this for the case with no noise. So this is the main result. Why is it the main result? First of all, it makes a very direct, it makes a relationship very clear between the height of the dip of the noisy coherent population trapping and the noise parameters of the environment. So what do I mean by that? So for example, if you remember the noise parameters inside alpha, specifically inside the correlation function, those can be determined one-to-one from the height of my coherent population trapping dip. So that's the picture on the right. So on the right, I'm basically plotting the excited state population as a function of my noise parameter. And for convenience sake, I just decided to write down the noise parameter in this form, right? Where alpha is the one that you know, and gamma E is just a gyroscopic, gyromagnetic ratio of the electron. It's just some number there. So as you can see, there is a one-to-one correspondence between the value of the noise parameter and the excited state population that you're supposed to see. And that is exactly why this result matters, because we can determine from this plot, or specifically the height of this plot, we can determine the value of the noise parameter of the environment. So that's the main result. All right, so before I go on, I really want to summarize what we've been doing so far. We've been working with a 3-level lambda system implemented in a specific medium. And what we did is that we derived a master equation that describes the dynamics of that system in not only quantum vacuum, but also some classical noise environment. This makes a good theoretical frame for coherent population trapping because it relates the steady state solution of the excited state to the height of the coherent, it relates the coherent population trapping dip in the noisy case with the noise value, with the noise parameter of the environment. So that's why it's important. And it's a one-to-one correspondence, which is very relevant. All right, so this is what we've shown so far. So aside from this, I want to tell you very quickly about another implementation of the theory of noisy coherent population trapping. And it's in initializing, or a so-called dissipative initialization into a specific state. So here's how to think about this problem. So let's say I have some state in my 3-level system. I start with some state, doesn't have to be in the 2 ground states, can be anything. And we know that if we were to drive our 3-level lambda system and we had the exact conditions we need, we can make a perfect coherent population trapping. And therefore, we can bring the state dissipatively to this state. It's a pure state, right? It's the dark state. And the coefficients are, of course, determined by the Rabi frequency of the lasers that we apply. So this is the relationship between the Rabi frequencies and the coefficients, as you see right here, of the 2 ground states. And phi is just the difference between the 2 phases of the laser. So this is something that's very well known in literature, specifically in the one that you see right here below. So this is something that's very well known. Now, what's missing from this picture is the inclusion of the effect of the noise on this preparation. So when you include the effect of the noise, you're going to get a noisy coherent population trapping. And as we know, the product of that is not going to be a dark state exactly. It's going to be slightly different. So then you can ask the natural question, well, then what's the fidelity of the state, the equilibrium state, in comparison to your expected dark state? And you can actually see how it looks like in the plot I've shown before, because since this is a perfect dark state and this is an imperfect dark state, in some sense, the fidelity will be related to the height of the dip in here. All right, so let me now show you a couple of plots to illustrate how the fidelity will behave. So this is the dark state fidelity. So the state that you're gonna get from initialization under the noise. All right, so the first thing to note is if you look at the first plot right here, it's the fidelity as a function of the Rabi ratio. Now remember, if I fix the Rabi ratio, I fix my dark state. If you go back, so the dark state is a function of the Rabi ratios, right? Through the sine and the cosine. And what I'm doing is that I'm implicitly taking this to be equal to 1. That is to say, there is no phase difference. So as soon as I determine my Rabi ratio, I determine the coefficients of the dark state that I'm targeting. So here on the x-axis, in fact, by mentioning the Rabi ratio, I'm really looking into different preparations. Each point here describes a different preparation of my qubit, or I'm saying the qubit, I mean the dark state. So that's what we have right here. And as you can see, there is a minimum in the plot where the fidelity is minimum at about, this is gonna be where the Rabi ratio is exactly equal to 1. So that's something that we see already when we plot the fidelity. And the reason for that turns out to be that at that specific state, that is to say the equal superposition state, the dark state gets coupled the strongest to the bright state. So what do I mean by that? So if you go back to this picture that I've shown, there's this alpha, right, that couples the dark state to the bright state. So that coupling becomes maximum if the Rabi ratio is equal to 1. And that's why the dark state that you're targeting becomes the one with the least fidelity when your Rabi ratio is equal to 1. So that's the explanation for that. Now I want to talk about the second plot as well. The second plot describes the fidelity as a function of one of the Rabi frequencies when you keep the ratio fixed. So now by fixing the ratio, I am fixing the target state. And since the ratio is fixed, I can vary both of them as long as I keep the ratio fixed, right? So, and I would then want to look into how the fidelity looks like. So there's a specific reason for this. So first of all, what you see is that the fidelity quickly saturates as you increase the Rabi frequency. So that's very important because a question for experimentalists is to determine what's a good Rabi frequency for them to use when they want to reach a target dark state. They don't want to use a Rabi frequency that's too low because, as you can see, the fidelity is small, but they also don't want to use a Rabi frequency that's too high. And the reason for that is because if you use such a laser with a high Rabi frequency, you might get some undesired couplings to higher excited states. Now, you can show that for an MV center, that's not going to be a problem until you reach maybe a Rabi frequency of about 50 megahertz or so, because of how the electronic structure of the Nitrogen-Vacancy center is. But for different 3-level systems, you have to worry about such undesired excitations outside of your lambda system. And that's why you want to basically pick the Rabi frequency that's in the beginning parts of the saturation. You don't want to pick it too high exactly because of that. And you're not going to get any advantage in terms of fidelity anyway. So it doesn't make sense to pick it in that sense as well. All right, that's all I wanted to say. So let me summarize. So what we did is a few things. First of all, we derived a master equation that describes the phenomenon of noisy coherent population trapping in a driven lambda system. We showed how we can estimate the parameters of the environment noise that we have from the coherent population trapping picture, or so-called emission spectrum. So also, you can also do that through the photon counts, they're all related. And the third one that we showed is a simple application where we dissipatively initialize into the dark state, and we see how the fidelity will change as a function of different states. So this is all I wanted to say. Thanks for your attention. And please ask me questions if you have any.
All right. Thanks, Arshag, for the nice talk. Any questions for Arshag? Feel free to unmute.
So I have a question. How can you discriminate the noise from your excitation mode, from the noise that you just described, from the noise coming from the detectors?
That's an excellent question. So that is one. Okay, so the answer to that is that is something that's left out of the research. I actually discussed that with an experimentalist. It turns out it can be done under certain, with respect to certain noises that you have within the experiment. But some of them are actually open questions. That is to say, I'm yet to look at them. That's a very valid point. I don't have a full answer for that. I need to look into it more.
And even in general, if you compare this, let's say the contributions from this noise, if you compare the contributions from this noise with the contributions from this other noise in terms of strength,
yeah.
like will they be comparable? One will be larger than the other, or
yeah.
Which one would you expect to be the dominant source of noise?
Right. My understanding. So when I asked the experimentalist, the one that was collaborating with us in this, not the project, but a more bigger project. You know what this is, the Murray project. So so my understanding from what he said is basically that there are certain noises where we don't really have to worry about in terms of their amplitude with respect to this noise, because those can be reduced by the experimentalist, but there are some that can't. So in that case, we do have to worry. We can go into the details about this, but it's quite a complicated thing when it comes to it.
Okay.
In terms of, like, I mean, describing it theoretically, I mean, it's complicated. It's gonna be a long word.
All right. If there's maybe another quick question, I think that would be okay.
Yeah.
Maybe I will. Yeah, I have one question.
Yes.
So
yes.
the alpha thing, when you discuss the fidelity, the alpha is starting from 0 and 1 to go down. No, fidelity it was 1 and go down.
Yeah.
And the question is alpha depends on omega 1 or omega 2?
Alpha doesn't depend on omega 1 and omega 2. No.
Yeah. Then the question is, if Rabi ratio equal to 0, when omega 1 is 0, yeah, that means your dark state is 0 state?
The dark state is the 0 state, exactly. It's only one of the ground states.
Right. But then alpha is still on, is it? Alpha
it is still on, yeah. Yes, it is still on.
So it cannot be completely dark state. The 0 state is not completely dark state, or no, 0 state is not completely 0. The fidelity would be different.
Well, that wouldn't be true, because you're basically turning off one of the lasers, so you no longer have a coherent population trapping to begin with. Right?
Yeah, but you can trap it in the 0 state. That's what it means by omega 1 equal to 0.
Yes, exactly. But yes, but we have to keep in mind that right. So okay, so can you repeat the question, Juan? I'm sorry.
I think I'm sorry to interrupt, but we're hitting the time, and maybe y'all can continue.
Yeah, I'll ask you later.
Yeah, that's fine. You can ask me through chat.
Arshag, there's also a comment from Ryan about an interest in doing an experiment related to this, so y'all should talk offline as well.
Yes. I'll look into the comment. Yep. Thank you.
All right. So thanks a lot.